now give a big mouth-sounding welcome to Amy Wagner.
Thank you guys for having me down. It's always a pleasure to drive down and be able to enjoy the view and see the ocean and whatnot. I don't get a whole lot of that in Sacramento. So what I'm going to talk about today is a couple different projects, and the overarching theme is the fact of using corals as a way to look at ocean and climate variability throughout time. In the intro, I said, through the Holocene, but when I'm looking at corals, most of these are going to be, modern. They're, 100 years old, although when I show you some stuff from some of the Ross Sea, deep sea corals, we have some pretty impressive ages of those. So real quickly, I'll just give you guys a brief. I know lots of different interests, and even though some of you guys may be familiar with coral, what we're going to do with this, how we can do this. I'll talk about Chuk and then the Ross Sea, and then at the very end, I'm going to make a big leap and see if there's any way that maybe we can actually even link some of these records in the longer term. So starting out, when I'm looking at this, we talk about analyzing hermatypic corals. And so these are not the traditional, if you go out in the Pacific, you're going to find a lot of bamboo corals and soft corals and sea fans and stuff. And these are very different. These are the large mounding coral heads that you see in the Caribbean. These couple examples here, my study site for my PhD was in the Gulf of Mexico, so this is a big mounding Psittacea coral head that's about 6 to 8 feet tall and big, huge, round guy. And so when we look at this, the coral itself is, it's a living organism, right? It's an animal, and so you have each of these polyps, and these are living in a community, and they're growing and building this large mounding head. So what we do is we take a core of these, we go out and actually drill into the coral head, and you take a slab and then you can x-ray them. And so this is a beautiful, one of the best examples of an x-ray of a coral slab, and you have these lovely annual growth bands here. So you have the dark high density band, which is actually in the summertime, and then you have the lower density band here, so this would be 1 year of growth. And then in this particular one, you actually have some of these winter stress bands, and again, this is from a Gulf of Mexico coral. So what's great about these is, we analyze the calcium carbonate, and if you know anything about isotope geochemistry, we look at the ratio of your oxygen 16s to your oxygen 18s, and we also get carbon 12 and carbon 13, but I'm not going to present any of that because there's a lot more kind of messiness to that because it involves the biology of the organism a lot. So when we measure the O16 to O18 ratio in the corals, these vary with two different things. It can vary with the isotopic composition of the seawater itself, and that is related to the salinity. So if you're in an area that has a fairly constant temperature and you see this variation in your isotopes, then it gives you an indication of maybe changes in precipitation or change of runoff and things like that. But the O18 that's incorporated into the coral structure, the skeleton, also varies with the temperature of the seawater. And so if you're in a place where both things are changing, you can get this where it's compounding on top of each other. So luckily, you also have strontium that's being mixed in, that's from the seawater, that's being incorporated into the skeleton. And if we look at the strontium to calcium ratio of the skeletal material, this varies with the temperature of the seawater. So now we have our two variables, temperature and salinity, and we have two ways that we can try to monitor these with our strontium, calcium, and our isotope ratios. So the first data set that I'm going to talk to you guys about is from Chuk Atoll in the Federated States of Micronesia, but it's also known as Truk Lagoon. It's basically was kind of the Japanese Pearl Harbor in the 40s, and so there's all of these amazing shipwrecks and one of the best diving places in the world. But we didn't go there for the diving of the shipwrecks, even though I did some of that afterwards. We went to collect the coral samples. So to put it in perspective where it really is out in the middle of nowhere. Flight to Hawaii, flight to Guam, and then over to Chuuk. And to put it into an oceanographic perspective, it's a really, really unique location. It was a great place to go to do research, but it was this fantastic oceanographically and atmospherically unique place. So Chuuk is kind of right in where this little white box is here. And this is the outline of the 28 degrees C isothermal line, which is basically the boundary of the Western Pacific warm pool. And Chuuk is right smack dab in the middle of this warm pool. And it's also in this area where the intertropical convergence zone migrates back and forth over Chuuk. So in the wintertime, the ITCZ is in the southern hemisphere, and Chuuk actually has very windy, dry conditions. And then in the summertime, the ITCZ is pretty much right on top of Chuuk, and that's their rainy, wet season. Not very windy, but lots of rain. So it's this fantastic little spot kind of right in here where there's the ITCZ, there's the Western Pacific warm pool. There's also a few oceanographic things that are happening if you look at it in the place where the currents are. And this is going to come into play later on. So you have just north of Chuuk is the North Equatorial Current, the major surface current. But then you also have the weaker North Equatorial Countercurrent that's kind of coming from the east towards from the west towards the east, right along where the opening of the atoll is. You have the trade winds. Okay. So this is also a region that's highly influenced by ENSO. So we not only have the ITCZ, we have the warm pool, we also have changes in El Nino. And being in California, we're all kind of familiar with the things that El Nino can do to the rain and all of that. Well, it's the opposite over there, right? During an El Nino year, it's actually pretty dry in the Western Pacific. The winds have slackened. And so you would maybe expect to see that this kind of warm pool to actually extend out more towards the east. So some previous research has suggested that the warm pool over the last few decades has been getting warmer. Okay? It's also suggested that the warm pool is getting fresher. So in essence, it's kind of suggesting more persistent La Nina-like conditions where you have greater winds, you have more of that warm water building up in the Western Pacific, and you have the ITCZ sitting farther north for more of the year, bringing a lot of fresh water into the region. Okay, so if you zoom in to look at the lagoon, this is actually, it's not a typical atoll in a geologic sense because there's a lot of these little islands in here. Moen is the main island, it's where the airport is, but this is a really large atoll with a few large openings. There's this really big one over here to the west, and then there's a couple smaller ones in various parts on the north and the eastern part of the atoll. So we went out and sampled at two different locations with this, within the atoll. And this was in collaboration, this was when I was a postdoc at NOAA Paleoclimate. And this was in collaboration with their KIOST now, the Korean Oceanographic Institute of Science and Technology. And they happen to have a research station on this little Micronesian island, and said, hey, we want to do coral research with NOAA. Do you guys want to do research out here? We said, yeah, of course. So we went out there and we collected some samples right out here in the outer atoll region. So basically, I'll show you guys some photos. We were collecting corals right where the water is blowing, because you have the wind that's blowing from the northeast, you have the trades, and it's pretty much just blowing the water in right over this region. We also collected some cores from right off the coast of this island here. Now the idea, and this is 10 or so kilometers apart to give you a scale. Okay, so just a couple photos here to show you guys. This is the what we call lobata reef, and we just gave it this name because there were all of these Porites lobata coral heads here, and you're like, oh, okay, we'll call it that. So you can see it's very shallow. This was about 13 feet of water. This is the outer atoll, even more shallow. It was only 8 feet of water. And at this particular site, we actually did 2 parallel cores on the same coral head. The first one that we drilled ended up being kind of at an angle, and we didn't feel like it was had a nice perpendicular line to the growth rate, so we went ahead and re-drilled that head. So we ended up with a total of 3 cores from this expedition. So what we've done with these, this is a student of mine that was in North Carolina, and you can see here the X-ray image of one of these, very different looking than the X-ray that I showed you guys earlier, because of a couple reasons. It's a different species, and also you don't have the huge temperature fluctuation in the Western Pacific as you do in the Gulf of Mexico. You go from 18 degrees to 30 degrees C, seasonal variation in the Gulf of Mexico. Out here, it's about a 2 degree C seasonal fluctuation. So you really don't see the nice annual bands, which makes it difficult to assign calendar ages to these. But we did our best. So this is my student, Jen. She just finished up last November, which was great. And so she did a bunch of different sampling lines along here, trying to sample kind of perpendicular to the, or parallel, sorry, to the growth rate here. And she did oxygen isotope analysis of these. She measured every 1 millimeter on the slab, and did oxygen isotope analyses at UNCW in Wilmington, and then sent off samples for trace element analysis, and those were done at the University of Texas in Austin. So the kind of the hypothesis around this of picking these 2 different sites was that if we have this inner atoll area here, okay, it's kind of protected, the wind isn't blowing, there is some circulation within the lagoon, but we thought that this might be a good place that we would really pick up on some of these seasonal variability, right? If you have a lot of runoff, and this is a volcanic island, and that's running off, and we should see a lot more change in salinity because of precipitation where it's close to this. Whereas the outer atoll should be much more representative of the open ocean, of the warm pool. So if you're getting changes, these longer term changes of warming in the warm pool and freshening of the warm pool, that's what we expected to see. You guys probably know where this is going is, in science, you don't always find what you expect to see. So this is some of the initial and early section of the data. We ended up, the cores were, the longest core was about 70 centimeters long. That went back to, I'll show you some longer plots here in a second, but went back to about the 1960s. But just to put this in a little bit of perspective here, when you're looking at this, if you're not used to looking at oxygen isotope values, the y-axis is inverted, so more negative is going to be warmer, and less negative is cooler. Strontium calcium is also inverted, so up is warmer and down is cooler. And then we do have some of the carbon isotopes on here. Like I said, they don't tend to be nice and neat. So, just basically just to show you what we would expect to see, that during the winter, that's the dry season, we would expect to see less negative O18. We would expect to see less negative O18 because it's cooler and also larger strontium calcium values. And we do. You can kind of draw the lines in here, and you actually do see that, okay, this is, these seem to be correlating somewhat. You can also look at some of the warmer periods, but overall it's not all that spectacular. We also looked at, correlations with rain, right? So if we said that if you are going to have more rain, wetter time periods, then you would expect to see the oxygen isotope values to also be more negative. And so you can see here that during your El Nino months, when you have drier conditions, you actually do tend to see less negative O18 values. So here's a couple of the El Ninos within this time period, and we're seeing these kind of less negative. Those tend to be some of these drought years in Chuuk. What was interesting is when we first looked at this, we saw this huge spike of precipitation here, which was a typhoon that hit the atoll. And we were really curious to see if we would pick up this big signal in the isotopic values. And it turned out we didn't see anything with it. But okay. So this is the outer atoll. There's a little bit longer of a time frame for this. Again, you have your warmer and fresher is less negative, or more negative, sorry. Cooler and salty is less negative. And we also have this plotted to sea surface temperatures from a 1 degree by 1 degree grid from this region, and sea surface salinity from the same area. So in some of the El Nino years, you're seeing these really nice coherent patterns. You also do tend to, in the satellite records, you see increasing sea surface temperature and decreasing salinity. And we do tend to see that same type of trend throughout the 90s and whatnot. But unfortunately, things kind of level off, and then in our isotopes, we actually see kind of a trend, a decrease. So what we did when we take this data, and we actually did try to put it onto calendar ages, and what we have here is we had a couple years of actual in situ temperature monitors. Okay, so they were monitoring the temperature within the atoll. And the blue line is the satellite SST data. And then the green is taking that relationship between the in situ data and the strontium calcium from the corals, and saying, okay, if it's, we plotted it, make a regression line, this is the relationship, now we're going to plug in our values and turn it into SST. And so this is our kind of reconstructed sea surface temperature record for that inner atoll, the one that we thought would really reflect more of those kind of seasonal changes. And the correlation, the R squared, is 0.53. And you can see there's some areas that have some good coherence, some areas not so good. We do see these strong El Nino events, okay, that we really do see both in the satellite record, maybe not so much the 97, 98, but we really do see a lot of dips in lower sea surface temperature in the atoll during these large El Ninos. For the outer atoll, the same thing, even more so, especially the 82, 83 El Nino, much, much cooler. But the overall trend, so this one goes back to the early 60s, the overall trend is, or the regression is, not all that great. What was interesting, that what we did, we looked at both of this by, kind of summer and winter. And what was interesting is you take the overall NSEP, the satellite SST record, okay, and you get the average temperatures. The inner atoll was consistently cooler than that satellite record, and the outer atoll was consistently warmer, which was opposite of what we expected when we were looking at this, right? We thought the inner atoll would kind of stay warmer because it's shallow, whereas the outer atoll is the one that's actually warmer than that 1 degree by 1 degree grid box that we used. So we tried to break this down and look at it a little bit more over time. And this is really interesting because, again, we see the big El Nino events, and then, it's kind of going back and forth around the average SST anomaly. But we really see this, since the late 90s, this big increase in the corals recording an increase in sea surface temperature, okay, in both seasons. I'm going to skip this because this is this is just a table showing the various correlations, and so the gray are all significantly correlated, but you guys can see that they're pretty low R-square amounts. So the last thing we did, I've kind of shown you guys all of the sea surface temperature stuff. So that was all based on the strontium calcium. I said at the beginning we can do the oxygen isotopes and try to pull out both temperature and precipitation. And so this is the residual. And what this is we took the temperature that we projected from the coral, that reconstruction from the strontium calcium, and then we said, what should the oxygen isotope be for that temperature? And then we said, well, how does the actual oxygen isotope value differ from what we say it should be? And so that's what this is showing. So that's the residual. So basically, if it's greater than 0, if the oxygen isotope value is greater than the projected, it indicates that it's going to be a saltier environment. And then vice versa, if it's less than, it's fresher. So there's a couple pretty interesting things about this. So you can see there, especially, so the red's the outer atoll. So there's a lot of decadal variability. We haven't done any of those kind of spectral analyses or anything like that to see what the significance of this is. But it's pretty interesting to see kind of this up and down, this decadal pattern in the outer atoll. And from this, we actually do see that since kind of 98, that there has been a progressive kind of, the outer atoll actually getting saltier instead of fresher compared to what some of the research or the published literature has suggested. The inner atoll really hasn't changed that much except for this 1998 El Nino, where they kind of converge. The inner atoll gets saltier, and the outer atoll gets fresher. And this comes back, oops, I thought I put the map back in here. This comes back to what the currents are doing. So we said that we have the equatorial current that's going to be kind of to the north equatorial current, that should be bringing water, the western Pacific warm pool, kind of pushing that into the atoll from the west. During an El Nino, that relaxes. So at this point, we suggest that we're really seeing the counter current being the more dominant water source at this time, because the winds have relaxed and we're actually bringing kind of fresher water in because the warm pool is more salty, and then the inner atoll is getting saltier because it's usually kind of fresher and you're flushing in a little bit more salty water, so they tend to converge during this time. But we don't have enough from the inner atoll to really kind of get before the 82, 83 El Nino to have the smoking gun on that. So some of our kind of basic conclusions from this work was, that we do see some of this seasonal variability with the sea surface temperature fluctuations. We do tend to see some of these 018 anomalies that are coinciding with low precipitation years. The outer atoll, we see some of these trends that are consistent with some of the published literature. However, because of the location, because the temperature fluctuation isn't really that great from season to season, the signal's extremely noisy. And it's really hard to, if we were to use this to try to go back in time and reconstruct, pick out former El Nino years, it would be really, really hard to do with this particular record. But one of the things that kind of came out of this as well is that a lot of previous coral reconstructions from the tropics, from these atolls, they go out and they pick one location within the atoll. And I just showed you some very drastically different records from two corals that were only 10 kilometers apart from the same atoll. And that if you're trying to, you have to frame your question, know what your question is, and purposefully go out and collect your samples knowing what all the variables are. Because you can't take a core at the inner atoll and expect it to be representative of that 1-by-1 grid box. And so that was, I think, one of the biggest things that we learned from this project is that we see very different signals from these samples. Okay. So as I said, I'm gonna make a little bit of a leap here and talk to you about some other more recent research that I've been working on. And you guys have all seen variations of the wonderful thermohaline circulation and all of this kind of stuff. So I'm going to talk to you about some work that I did on some deep sea corals that are down here in the Ross Sea. And at the end, I will try to come back and link maybe some of these Micronesia corals to some of these deep sea corals, but like I said, it's a little bit of a leap. So to switch gears, to go from nice, warm, sunny, tropical diving to Antarctica, if you look at the circulation of Antarctica, you have your Antarctic circumpolar current that's going around towards the east, and then you have the east wind drift that's a kind of a counter current here, and so the Ross Sea, the corals that we sample, they're kind of right here. So okay. So, and then your cross section this is also an area where you're going to have, with the the east wind drift, you're having a lot of water being pushed off the shelf. This is very salty water, right? You have that high salinity shelf water because you have sea ice forming, and then you also have circumpolar deep water that's coming up towards onto the shelf. Excuse me. So some previous work has shown that there's a possibility based on radiocarbon data from these deep sea corals that there's this freshening of the Ross Sea. And this would be due to the fact that you're getting, if you have this high salinity shelf water, okay? And that's because, again, the sea ice formation. That's being pushed offshore from the katabatic winds, and the circumpolar deep water that comes up is going to be a lower salinity. So there's the hypothesis that there's this weakening of the winds. There's an increase of the winds that's pushing more of that shelf water offshore and causing more upwelling of your circumpolar deep water. So we went out and tried to collect samples from both kind of on the shelf so that we could see if there's a change in the shelf water geochemistry, and then deeper down samples that would have been bathed in only circumpolar deep water. So I did this on a Korean research vessel, which has absolutely no relationship to the fact that I was doing a Korean project in Micronesia. It just happened to be that way. So I spent 8 weeks on the icebreaker Aeron, South Korean icebreaker. And we went down and did these 4 dredge sites. So these are the 2 that are going to be on the shelf. They're around 500 or so meters. And then these 2 sites are around 1,500 meters or so off the shelf. So again, the idea that these will have been in circumpolar deep water. And if we're seeing more of that circumpolar deep water being upwelled onto the shelf, we would see a change in that geochemistry. And then also, I'm going to go back and show you guys this one. You would also see this change in radiocarbon. It's older water because it's deeper water, and so there's this idea that, you know, this freshening, this deep water that's coming up is actually making the coral, it's being recorded in the radiocarbon ages as being older. Okay, so again, a couple photos to show you guys how we were doing this. This is not the way to do this. I will say that right off the bat. This is a dredging, a dredge. And we put this over the back and dropped it down onto the seafloor, and we towed it for about 500 meters and then pulled it up and had picked up everything off the bottom in that 500 meters. But this is what we had in one of our dredges. Our first one came up almost empty, and then this one came up and it was like Christmas. So lots of sponges and other critters, some rock, very few rocks, but some rocks. All of this pink stuff is various species of deep sea. Again, a scleractinian, a hard skeleton coral, okay, not one of the soft proteinaceous type bamboo corals. And then lots of there were biologists on board, and so everybody was kind of, oh, here's a brittle star, that's for you. Here's a coral, that's for you. So here's a close-up of one of our best samples. You can kind of see a size. So it said, not the way to do it. A, it's probably, pretty destructive environmentally. And B, you can see that most of these pieces are in very small chunks. Right? We didn't get very many nice big whole samples like this one. This one, because it's that nice bright pink, it was alive, so we can assume that the stuff on the tips would be modern, and then going back in time. Not a lot is known about these types of deep sea corals, not even their growth rates. It's estimated that their growth rate may be around 1/4 of a millimeter per year. So if you use that growth rate, this would be about 1,000 years old. Some of our initial work has suggested that they may be growing much faster than that this is only maybe a couple hundred years old. The other thing is this little dot here, that's a snowflake. It's completely foreign to me to be collecting corals in the snow, but it worked. Okay, so here's another close-up. So, these are colonial, just like those big mounding coral heads. And so all of these little bumps, those are the individual polyps. It's just a much different type of coral than what I had been familiar with working with. So on the ship, we did a little bit of subsampling. I used a Dremel and tried to drill every 1/2 centimeter or so to get some powders for isotope analyses. I did this cruise, it was 2 years ago. It was actually on the ship 2 years ago now. Most of the samples are still in Korea because we've had some problems with customs and permitting issues and things like that. So we haven't had a chance to do much with these yet, unfortunately. These are some of the ones that we did get to bring back. So with some of the customs and the CITES is the fossil pieces were okay to bring home. And these pieces, these were from, let me go back, this pink guy is from one of the sites that was on the shelf. This is, we think it's what's called an arena fissurata. These are from one of the deeper water sites, okay? These were clearly fossil. This one down here, as it came up, and I was like, why are there a bunch of sticks in the dredge? You know, and I had to go find some hydrochloric acid and put it on it to see if it really fizzed, if it was carbonate. And it did, so you know, it was all good. But we have not been able to make any kind of identification of what species these are. But we have taken them and done some radiocarbon dating. And as you can see, they're pretty old, and there's a pretty big range of samples going from 6,000 years before present, 16,000, and up to 46,000 years, which is right near the edge of radiocarbon dating abilities, which has been pretty exciting. And this is just a distribution of some of the ones that we've done. So all of these deep water ones on where the circumpolar deep water would be has this really big age range. And so the plan is to do a lot of these same type of geochemistry to monitor some of the deep water circulation. The shallow water ones up on the shelf have all been consistently within a few. I think our oldest was around 5,000 or 6,000 years old, which is still pretty impressive. So I said I was going to kind of circle around and come back to making some kind of link between these. What's the overall, okay, we've got these different sites and whatnot. So if you look at the two sites where we're at, okay, if you have changes in a longer-term trend in El Nino patterns, for instance, okay? If we're maybe going into more of a long-term La Nina state where you have greater winds coming, greater northeasterly trades, more fresh water forming up here, what might that do to the larger thermohaline circulation? And the effects would be felt in this part of Antarctica with the circumpolar deep water, or the Antarctic circumpolar current. And so if you end up having this, if this is enhancing the winds, that should enhance the amount of high salinity shelf water that's getting pushed off of the shelf, that's increasing that circumpolar deep water, upwelling, and kind of changing some of these different masses that we're seeing. So, like I said, it's a really big kind of leap, but we'll kind of play around with it and see where it goes. So as I said, that's just a couple examples of some of the things that can be done with these types of corals. With that, I finished a little bit early. These are just a list of a bunch of my colleagues and collaborators in different places that we've worked and done. And as all of you guys know, all of this takes a lot of help and effort from students and grad students. And I've actually been at mostly undergrad institutions, so lots and lots of undergrads that have volunteered many hours drilling corals for nothing but being able to put a line on their resume. So, with that, I'll take any questions. Yeah.
So your choice of being at Truck Lagoon, was that simply just logistical feasibility? They were already headed there and you got invited, or is that is it less opportunistic and there's some strategy as to why that would be a good place to be doing those courses?
It was completely that they said, we're going to go here. Do you guys want to do, we want to do some coral work. Does NOAA want to participate? So it was that opening. The choice of what we decided to look at, initially they had somebody who wanted to look at can't even remember, like plutonium or something like that, trying to track plutonium in the current, the North Equatorial Current. So since he was not on the project anymore, we decided that, hey, this is a really great opportunity to try to do some of this warm pool work. So it's kind of both.
Are there other cores in the area, in that vicinity, that could be used as replicates for looking at that warm pool phenomena, or is yours scanned out?
Unfortunately, no. We wanted to try to get back and actually collect some in the more western part of the atoll to try to get that counter current, but it never worked out logistically to get back. They don't have a big enough boat to be able to go out that far, and yeah, so.
I have a question about the first case study you presented. So you were showing actually, I was actually curious about the first coral slab that you showed from California, where you actually worked on that one.
The very first, the nice one?
Right. But my question was about dating the one from the Pacific. So the banding was very narrow. So and also it looked like there were lots of bands. So are those annual? Or?
Yes. Yeah. So. Yeah. So, right, so this is from the Gulf of Mexico, and yeah, these are annual, so this is about 50 years of growth, and this core is about 200 years long, and that's from the Flower Garden Banks National Marine Sanctuary in the Gulf of Mexico, and it's, like I said, it's a couple reasons. It's a different species. It grows much faster. So you really see when it slows down, it's summer growth because of spawning. You get those high density bands. And it just, because the temperature variability, you have these really nice seasonal signals. So when you get into the tropics, the coral isn't growing as fast. It's not getting those big seasonal signals, and so you don't end up having those nice bands. So with this, it's easy to date it. You can see it, and you can go through and assign, I know that this distance based on the X-ray, that's so many years because I collected this in 2005, whereas the other one, we had a lot of difficulty trying to put an age. So to do the other one, what we did is we did do the wiggle matching with both the strontium, calcium, and the isotopes to match the seasons. Yeah. Yeah. Yep.
And it's also why did you check also magnesium and magnesium calcium ratios as well? Or just
we did, but since the corals are aragonite,
right.
Magnesium calcium doesn't work for them.
For those deep corals from Antarctica, can you also section those and see annual growth patterns, or is it?
You can see on some of them that are large enough, maybe the stalks are about as big around as my finger, and you can see some rings. They're more like trees in that sense. And I actually have a student, an undergrad, that's going to be doing a project where she's going to take a bunch of those and section them, and we're going to go do nanosims on them to try to, like I said, there's not any publications out there about how these grow. So that's, I think, the first step that we're going to do is trying to document that so that we can tell, because if they're growing like a tree, they're growing out, but they're also growing up. So that doing little puncture holes up the stalk isn't really going to give you a good age or, a time. So trying to figure out how we should sample them to get a good distribution of time is the first step. Yeah.
I was just wondering if you expect the signal in Antarctica to be stronger than what you saw in the warm pool, and if being deep will help you extract a signal.
That's a good question. I think To be honest, I don't know for sure what we expect to see in the ones from Antarctica. The initial idea was to go and just try to do the radiocarbon and see if we can see changes in those water masses. But I think based on the early work and then based on our radiocarbon ages that we got of the deep ones, I don't think that's going to really help us that much. So we put in a proposal to do more high-resolution dating, like uranium, thorium dating, and then try to do a bunch of the, ICP-MS, trace metal geochemistry. But it didn't get funded, so we're going to try again and see what we can do with them.
What are the issues about permits to not get these things from Korea? What's the holdup? I mean, it's clearly science can't go ahead if you can't get access to sample.
Right. The big issue is a lot of it is simply a language barrier. We need the permits to be issued from Korea because the CITES requires an export permit. And since they were on the Korean ship, they went back to Korea. They're going to be exported from Korea. And nobody seems to think that it's a big deal that they don't want to go through the process of getting the permits. And I'm just too nervous about trying to import them without the permits. So I saw one of the guys at AGU, and he's like, you should just come to Korea and take them home with you. That maybe that'll work, I don't know. So I don't know exactly what our plan is right now.
Whose jurisdiction is the area where they were collected, the Ross Sea area? Is it international?
It's international, yeah. So we didn't have to go through that to be able to collect them. And like I said, when we exported the dead ones, the fossil ones, it didn't matter because I had all of the paperwork, like, okay, within CITES, fossil corals are not subject to this. And it really depends on who's looking at the samples, right? I mean, as a lot of you guys probably know with various things, it really depends because if you get a customs person who is like, oh, that looks cool, like coral, then, it's not worth the risk with the permits. But yeah.
Because she was kind of back from Cuba, and she had a little piece of light coral, but she bought it in the market, on the street market.
Oh, really?
Yeah, it was an arrest, and she didn't look really stopped.
Yeah,
She
yeah.
had to go back to the job, and
Yeah, so it's,
so yeah, don't do it.
no.
So,
But
the
yeah,
fossils
and then,
wasn't a problem, right? The old one, the fossils, that was.
right, yeah. And it's really a gray area because you could argue, well, they're fossil now because they're dead. But again, it just kind of depends. But yeah, so we just haven't we want to make sure that we have all of the paperwork in order. And then one of the things I was actually going to mention that, it said that doing the dredging is not the ideal way to do it. Trying to use ROVs, trying to use submersibles is definitely the way to be able to try to do this kind of work so that you can actually see what you're collecting. You can get large samples, you can get whole samples. And I did a Alvin training cruise last summer with Stephanie, who's here in the audience. And where we actually did get to go in the Alvin and learn how you do that, and we collected some different types of deep sea coral samples off of Massachusetts. But it was it's a much more elegant process than putting a dredge overboard.
With a dredge of 500 meters, is the assumption that all the coral you picked up were from in situ, so at least they're all from the place. They couldn't have gotten there by any other means, like an ice debris or anything like that?
No, the ones that are the deeper site that are really old, they have been dead for a really long time, so they are not necessarily in situ. That's another problem, is it would be nice to be able to see if it looks like a debris flow and whatnot, so that's another question.
Well, are there any other questions for Amy? All right, well, it is happy hour, and she is going to stick around to be happy. Feel free to ask her any questions about what she presented or anything else, and please enjoy the beer from the brewers. Thank you.